Hi, we're Crater, Caltech's first ever collegiate rover team. Over the last year and a half, our team of 15 undergraduates has been hard at work designing, building, and testing our rover, Ernie. We hope to keep developing Ernie on our path to CIRC at the end of the summer. In designing such a complex system, we've had to split into 5 separate subteams: mechanical, manipulator, electrical, software, and science.
The Crater Drive-In Chassis subteam's main objective was to design, manufacture, and test a robust mechanical design capable of reliable performance across a wide variety of terrains. To that end, a rocker bogie system was selected due to its low mass and complexity, stability across extreme terrains, and flight heritage. Now, on our second mechanical revision, we prioritize low mass and complexity. With no permanent welds or rivets, the rover can be augmented as necessary, giving us freedom to continue development on the chassis. 24-centimeter inflatable wheels were modified to provide necessary traction in navigating everything from sandy to rocky environments. The differential bar aids in traversing rocky terrains, balancing the rover and allowing it to scale obstacles of heights up to twice the wheel diameter. With Maxon brushless DC motors, the mechanical design is optimized to provide a dependable platform for other subsystems to build on.
The manipulator arm is designed to have fine control while still able to lift large loads up to 5 kilograms. To maximize flexibility within task space, 6 degrees of freedom were given to the arm with an extra 2 degrees of freedom on the end effector, providing grasping and fine mobility. All arm joints contain motors employing field-oriented control, enabling position, velocity, and torque mode control. The end effector uses 2 servo motors, allowing the gripper to impart controllable forces, enabling delicate manipulation for items such as switches. Alongside this, a worm gear stage on the gripper also minimizes current when lifting heavy objects. We have successfully assembled an ARM prototype, but are continuing to work towards a fully machined ARM by the competition this summer. All joints have been engineered with machinability in mind, so we are well on track to fabricate and integrate the ARM by the end of June. The end effector has already been fabricated and only needs further testing to be competition ready.
The rover communicates with the base station over both a 2.4 GHz Wi-Fi link and a 900 MHz long-range radio. The Wi-Fi link is used for transmitting videos, while the rover is in a closer proximity. This frequency is implemented using a Ubiquiti Rocket M2 with a 120-degree sector antenna at the base station and an omnidirectional antenna at the rover. The 900 MHz frequency is for sending drive commands, remotely disabling the drive system, and receiving data from the rover, such as battery cell health. For this frequency, we use an Adafruit feather with a LoRa chip. We've conducted testing across campus to ensure the integrity of the signal across varying distances and through varying obstacles. The electrical system on the rover is designed with efficiency, robustness, and safety in mind. The system is powered off a single 7S LiPo battery to provide 25 volts with 8 amp hours. The battery is located in the back compartment so it can be switched out easily and is continually monitored by an off-the-shelf battery management system, or BMS. The BMS includes active balancing of cells, over and under current protection, and over and under voltage protection. Before the rover drives, we set values for each of these protections via Bluetooth and manually control discharge behaviors. While the rover is driving, we can communicate to the BMS via RS-485 to UART converter to the Arduino for receiving data on the cells. We have a contingency plans for any disruptions to the batteries. Through either the physical press of a button or through a remote command to the BMS app, we shut off the BMS, thereby disconnecting batteries from all loads. Fuses are also included throughout the system to protect each load. Fuses are placed at the output of the batteries, as well as the input and output of each DC-DC converter.
The software team has prioritized closed-loop driving and ARM motor control. All motors are controlled over CAN bus and use open-source ODrive S1 controllers. All controls are managed through ROS, the robot operating system, allowing for signals to be sent and received over the comms network. We control the driving of the rover using an Xbox controller. As for visual feedback, a RealSense D455 camera is connected to the front of the rover, providing an RGB, depth, and active IR image. Much of the work leading up to CIRC will focus on fully testing and integrating closed-loop driving and ARM control alongside beginning autonomy effort. For the science sub-team, we are working on camera modules for rock identification and regional panorama captures. In the near future, we will begin testing for natural oil traces such as keratin, allowing us to complete the CIRC science testing. As shown, our rover has come a long way from last year's CIRC, and we are excited to attend this year's competition to demonstrate our progress. We will continue development through the summer to ensure we are as prepared as possible by the end of June. Thank you for your time and consideration.